Hello and welcome to another episode of That 60s Recording Podcast, the podcast that has conversations inspired by the golden era of recording. Okay, so I'm going to start a very slightly different series of podcast episodes, and I will warn you, they are sort of technical. I know that there's a mixture of listeners to this podcast, sort of people that are generally interested in 60s music, and then there's musicians and producers and engineers, and all sorts. But this series of lectures is more geared towards people who are interested in studios and sort of the technicalities of recording. That doesn't necessarily mean that you have to be doing any of those things in order to enjoy this. You might just enjoy picking up a few nuggets of information. Anyway, so Ted Fletcher, who I spoke to a few weeks ago on the podcast, has a series of lectures up on his website. And I, being the nerd that I am, printed them all off and got my highlighter pen and started highlighting them all, just because I was really keen to learn. I'm always really keen to learn as much as I possibly can. And as I was doing it, I thought, how many people realistically are going to do what I'm doing? Not that many. You know, everybody's really busy, rushing around, sort of living life. So I emailed Ted and asked him whether he would be okay with me reading the lectures out for all of you guys. And he was absolutely fine with it, which is typical of the character that you can see coming through in my episode with him, the interview episode, that is. The lectures cover a wide range of topics, all to do with sort of the technicalities of the recording process. They are quite technical. Ted's obviously extremely knowledgeable about sort of electronics and audio electronics and that kind of stuff. So it might be that I count myself in this category, by the way, that you pick up 50% of what's going on, or it might take you a few listens to really understand what's going on. And there's likely to be things in there that you know already, but as with anything slightly academic, there's a lot of context going on. And it's really important to just sort of go with the flow for a while because it all wraps up back in the end. I've loved it. I've really loved it. I love getting into the mind of someone of Ted's capacity. You know, he's such an intelligent guy and he's done some incredible things. You know, that the Joe Meek compressor he designed is legendary. You know, it's absolutely legendary. And to get in the mindset of somebody like that through an interview, you know, like I did with him before, but also now as a lecture series to really understand, you know, when he sits down to design a compressor, what's he thinking about? Where has this all come from? And of course, he's had so much experience working with Joe Meek himself and doing a lot of the other technical things that he's done throughout his life. It's just a really rare opportunity to get a window into his mind. And hopefully it's easier for you, now that I've had a chance to sit down and read these and record these for you, to just absorb them, rather than having to sit on your computer screen and read through them. That's the idea anyway. I really do hope that you get something from it. You know, it's been absolutely brilliant for me to sit and read through them all and then have to read them out. You know, I really enjoy it and I love listening and learning about these things. And my philosophy with this podcast has always been, if I enjoy it, then my hope is that you guys will enjoy it too. So yeah, this will be, I've got the pile of lectures here next to me. I think there's about 6 of them. So this will be the next period of time's worth of episodes. If it's not for you, then I'm sorry. Maybe you can just dive back into some of the old episodes. I don't know. Anyway, this is what we're doing. And Ted did ask me to put a caveat sort of on the front of these. He's asked for me to just make it clear that these were written sort of 20 odd years ago. And although they're quite accurate, they were written to be delivered at universities. So they do skip a lot of sort of technical information. As with anything, you could pick apart all of the little nuances of every sentence and you could provide context for days. But he just tried to condense it all to one lecture. And there was also moments in the lectures that when he delivered them where he went vastly off topic and took questions and all that kind of stuff, which we're obviously not able to do here. Although I'm very sure Ted would be willing to answer any questions. You know, maybe if you do have some technical questions based on some of these episodes, you could get in touch with me and we'll do a Q&A episode if it comes to it. So yeah, just bear that in mind when you're listening to it. Okay, So here we go. This is lecture number 1, which is entitled Good Sounds, Equalizers and Compressors. At risk of just blabbering on even more, I haven't done a huge amount of reading of stuff, I'm not, I don't have a contract with Audible or anything like that. So I've tried to read it in the clearest, steadiest paced voice I possibly can. I hope it's acceptable. Just listen to the information, don't listen to me. Right, enjoy this, and I will speak to you at the end. So what makes a good sound? You'll spot straight away that this question doesn't have a simple answer. In fact, I'm sure it can't be answered at all. What do we mean by good? I want to treat good as being pleasant, natural, and acceptable. Our ears are used to hearing sounds in the natural world, particularly human sounds and speech. Record. When we record those sounds and play them back, we want them to sound either as natural as possible or like a nicer version of the original sound. So, to be practical, let's look at the recording process and see what happens to the sound, see what is important and what's not. A recording of speech needs first a microphone, and that mic has to be placed a distance away from the mouth of the speaker so that the speech will sound natural. Immediately, we are faced with a compromise. Because of the way our hearing works, we're used to hearing speech at a distance of about 2 meters. But if we try to record at that distance, we start to pick up too many sound reflections from walls and other objects in the room. So to compromise, the mic needs to be closer. So we choose a distance of around 20 centimeters. That keeps the speech louder, cuts down on the outside noise, but also changes the character of the speech because of the very close proximity. It tends to make the low frequencies more pronounced, but that's not too serious and certainly not unpleasant. We have assumed that the microphone is a good one, say a TFPRO GP, a large diaphragm capacitor mic with a good extended response. That speech signal from the speaker is being converted into very small electrical signals that go to a mic preamplifier. This needs to get the signal high enough to feed into the recording system, whatever that may be. For the moment, we will say it's a computer sound card and a lump of flash memory. It's here at the mic preamp that we hit the real first critical problem area in the system. The vast majority of microphone amplifiers nowadays, including those called valve, make use of so-called specially designed low-noise audio amplifier ICs. If you're an engineer, you may look up the recommended application circuit for an IC, together with its specification, and, because the manufacturer dearly wants you to use his chip, you will be very happy with the simplicity of the application circuit and will marvel at its low noise, low distortion, and general performance. But sadly, there's a whole lot that the IC manufacturer doesn't tell you. In fact, there's a whole lot that even he doesn't actually know about his own product. If we could use the IC in the way that the manufacturer intended, then it would perform wonderfully. Of that, there is no doubt. But the real world isn't quite like the test lab. Those electrical signals coming from the microphone are at a volume level of, say, -60. This is a very loose way of talking, but it's best to try and keep it simple. Which means that the operating level of the signal is at -60 dB. So the signal to get up to an operating level of -4 dB, which would be a reasonably sensible level for a digital recording, one would expect to need to set the microphone preamp to have a gain of 56 dB. Fine, that gives us the right working level, but there's a problem. Although the speech from the microphone is at -60 dB, the sound of the S's and T's produce momentary voltages that would relate to a peak level of nearer -25 dB or even higher. Those transient peaks don't sound loud because they are of such short duration. The T and K consonants are the worst offenders. Clipping. You might say, but if you don't notice the peaks, then why not clip them off? And that's a perfectly good idea, and in practice, that is what happens. But we're moving too fast. We have a transient of minus 25 dB, and the gain of the preamplifier is set to 56 dB. That means that the transient is going to come out of the preamp at a level of 56 dB above minus 25 dB, which is now plus 31 dB. Now, even ignoring the fact that our recording system could not handle anything like that level, the preamp will have given up trying at about plus 22 dB, i.e., it has clipped, reaching the maximum output it is capable of. And this is where the IC designer ought to be learning a lesson. When the IC is operating within its limits, the distortions are extremely low. But if the IC hits clip, technically the signal hits the rail and negative feedback ceases to work. Again, that's fine, but the problem comes in the first few microseconds after the overload. The IC is struggling to get back to normal, and in doing so causes very short-term distortions to the audio that the IC designer never sees, and he would ignore anyway because it's outside the specified operational conditions. So to sum it all up, two transients happen when our speaker says cat. The transients are so short that we don't hear them, but the mic preamp momentarily clips and the normal parts of the speech immediately following the transient are distorted, only for a moment, but it's enough to be noticeable as something not quite right. This instability-induced distortion is subtle in its effect, but is one of the main reasons for the difference in warmth of sound between different mic preamps. Once the audio signal has got out of the mic preamp, whether we like it or not, its dynamic range has been reduced, because those annoying transients have been clipped off. So now the quality of the sound is affected almost totally by straightforward harmonic distortion, the frequency response, or bandwidth. Distortion. When we talk about distortion, engineers mean harmonic distortion, the way an amplifier subtly alters the shape of the audio signal. In nature, and in physical musical instruments, all sounds could be called distortions of pure waves. And all these distortions affect the frequency in a one-sided way. That is, the top of the wave is squashed more than the bottom, or vice versa. This type of distortion adds harmonic content to the sound in a musically pleasing way. It's called even-order distortion. In integrated circuit amplifiers, the arrangement of components is symmetrical for the top wave and the bottom wave. This means that any distortion that occurs is also symmetrical, but this is not a natural sound. The effect of the ear of this third harmonic or odd order distortion is extremely unpleasant, and very slight amounts of it can be heard. When there is distortion just discernible, the sound starts to be brittle and ragged. Higher levels of distortion sound as though the signal has been treated with a cheese grater. Bandwidth. But let's assume we have a really fine mic preamp and we have minimized all these distortions. How is the signal sounding? We're taught that we hear frequencies between 20 Hz and 20 kHz. We're taught wrong. Those figures are a comfortable compromise, but don't really mean a lot. At the low frequency, we can recognize with our ears frequencies down to about 30 Hz, although there's no clear cutoff. More importantly is the fact that we experience low frequencies from about 100 Hz downwards with the whole of our bodies. So frequencies as low as, say, 8 Hz are important if we're trying to achieve realism. At the other end of the spectrum, we can hear up to around 12 kHz clearly, although this depends a lot on how many beers you've drank the night before. At 12 kHz, the sound is audible, but the quality of the sound is not discernible. Above 12 kHz, we can tell that there's something there, right up to 20 kHz and even beyond. In the mid-ranges, the ear is amazingly sensitive to the tiniest effects of distortion or phase shifts, particularly around the 30 kHz region, and incidentally, this is where a great deal of directional information is used by the brain. A signal source that is off to one side can be pinpointed because of the minute time difference in the sound reaching the two ears. I did some experiments on stereo direction sensing back in the mid-80s and proved conclusively that it's actually phase, in the form of time difference, that gives us most of our direction sensing ability. In short, The ear is fantastically sensitive to being fooled in the mid-ranges, that is, say 500 Hz up to 3.5 kHz. Outside those frequencies, it's less particular, but there are some odd effects to do with extremes of bandwidth. Restricted bandwidth. It's an interesting experiment to find out what happens to perception when bandwidth is restricted. Listening to any sort of speech or music, if the bandwidth is restricted at the bottom end or top end, it is instantly recognized. However, if the bandwidth is restricted in a controlled way, removing low frequencies and high frequencies equally, then the result to the ear is remarkably acceptable, even when the restriction is severe. This effect has been very useful in the past. In the cinema, the bandwidth of optical film was about 150 Hz up to about 4.5 kHz, and lumpy at that. But it still sounds acceptable because the signal was filtered top and bottom using the Academy filter. Practical bandwidth. So what would be a practical bandwidth for digital recording? It depends on what you're trying to achieve. I think it's possible to set the bandwidth to suit the program. There is no point in extending the bandwidth below, say, 30 Hz if the end product is likely to be listened to on small radios or in cars. The problems are not only in what's possible to hear, but also a physical problem with loudspeakers. The distance a loudspeaker moves is inversely proportional to the frequency. So if the cone moves a distance of 0.1 mm at 1 kHz, then at 100 Hz it will move 1 mm, and at 10 Hz it will move 10 mm. So extended frequency responses may sound attractive, but they are not very practical. If the bandwidth is limited to 30 Hz at the bottom end, then the high frequency end should also be limited to about 14 kHz, so that the sound remains balanced. Equalizers. Friend or foe? I have talked about quality and distortion and made some comments about bandwidth. So how do we engineer or alter the sound of our recording? The first device to spring to mind is the equalizer. Equalizers came from the film industry. The very name gives the game away. The purpose of the equipment was to equalize the sound between various takes, where the microphone may have been different distances from the person speaking. The first equalizers were simple tone controls where the sound engineer could alter the weight of the recording, but almost immediately engineers recognized that the most useful sort of modification to the sound was some sort of lift in the upper mid-frequency band. They found that by altering the intensity of this area of sound, they could achieve an element of distance effect. The first commercial equalizers were of the Pultec type. These were passive circuits that bent the response, followed by an amplifier to make up the gain that was lost in the process. They were basic circuits dealing with two selectable frequencies. You had the choice of boost or cut on each frequency, and the bandwidth control that operated on both frequencies. But it was all a little hit and miss. In reality, a great variety of sounds was possible by combining boost and cut at single frequencies. What this does is to introduce variations in the phase response, which has profound effects on the sound. Equalizers as we know them have their roots in hi-fi tone controls from the 1950s and 60s. In the mid-50s, an engineer working for EMI at Hayes just outside London, a man called Peter Baxendale, had an idea for a circuit type that had some supreme advantages over anything that had been around before. It was a circuit that could lift or cut frequency bands and apply phase shifts that were very close to those occurring in nature. Because the circuit worked by modifying electronic feedback, it was very controllable and did not need make-up amplifiers. The basic Baxendale equalizer is simply shelving high-frequency and low-frequency curves controlled by two rotary controls. Both the low-frequency and high-frequency have little or no effect at the center frequency, normally around 1 kHz, but have increasing effect out towards maxima at about 100 Hz and 10 kHz. But there are many variations on the Baxendale circuit, including mid-frequency boost and cut sections. This is probably the best and most natural sounding circuit configuration for an EQ. More violent and much better on paper are the state variable filter equalizers. These are based on clever filter electronics where it is possible to tune circuits to precise frequencies and vary the Q, quality factor, of the peak. This sounds fine in theory, But in nature, there is no sound that contains high Q values. Anything modified with these circuits runs a high risk of sounding awful because of the confusing effect on the ears. Similar things can be said about many of the gyrator-type filter circuits that abound in so-called professional mixers and equipment. They can be made to operate at high Q values, but by doing this, the phase relationships in the signal are sharply altered and the ear is easily confused. But some form of EQ is necessary to pull instruments forward in a mix and to generally tailor the sound in both mixing and mastering. For general purposes, where just a little alteration is needed, then the simple Baxandall type is best by far, and most mixer channels are fitted with these. But where there are tunable mids, beware of overuse. In mastering, a much more specialized form of EQ is required, one where one can control bandwidth and produce shifts in tonal balance while being sure of retaining phase relationships and so a clean and transparent sound. My own P9 EQ is designed precisely for this purpose, with Baxandall-based high-frequency and low-frequency controls, but with the addition of selectable frequencies and two mid-frequency sections where the peak is determined by a passive inductor-capacitor combination. To make the whole process repeatable, every control is a calibrated switch. At the risk of sounding really boring, I have to repeat what you must have heard many times before. Don't use an equalizer unless you have a clear idea of what you are doing or trying to achieve. Distorting. Using an equalizer is distorting the audio signal. It's changing its spectrum, altering the relative loudnesses. Gentle use of equalization will pull sounds forward or push them away. Any more violent use will cause confusion to the ear and destroy the illusion that the brain has created. It's almost like looking at one of those three-dimensional computer pictures that you have to train your eyes to see. Once you see the hidden image, it's clear as anything. But if anything disturbs you, the image collapses and your eyes see chaos. Of course, there is a place for more extreme equalization. It's in effect where you'll be trying to get a particular guitar sound or make the piano sound even more striking. And yet, isn't it strange how often you think you can achieve an effect with just a bit more EQ, yet when it comes, it really doesn't work. All you achieve is brown mush or grating distractions. No, the best engineers are very sparing with the EQ. They use very small amounts of tilt to achieve positioning and detail, but they rely heavily on microphones, microphone placing, and good performance to get good recordings. Compression. During the mixing process, the three factors which most affect the placing of the sound in a mix are relative levels, relative frequencies, and compression. The relative levels are taken care of, obviously, in the mixing process with faders. The relative frequencies can be adjusted to some extent with EQ. So we come to the most neglected factor, compression. Now, we are not talking about compression as a method of reducing dynamic range here. That's a function of compression where the aim is to make the effect as transparent as possible. It's just to fit the signal into the available dynamic range on the medium you're working with. Very briefly, this is best achieved nowadays by some very clever computer algorithms that operate independently on different frequency bands, yet are timed cleverly so that they are not noticeable, except for their dreadful misuse on Radio 2, where the voices of the presenters make me cringe. What we are talking about is three areas of compression. Compression of individual signals, instruments or voices, group compression, and overall compression. I'm going to be just a little controversial here. Most recording engineers try to record the human voice completely flat with no effects, so that any required effects can be added later during the mixing process. When I record a solo voice, I usually use a little compression. The reason is that to make a voice audible in the mix, some compression is always necessary. But the real reason is probably that until very recently, it was not possible to record the true dynamic range of a voice at all. The purpose of individual signal compression is to stabilize their position in the mix. If you have read any of my writings about compression, I generally go on about the automatic biological compression effect of the ear, how our ears turn down loud sounds. My compressor designs try to imitate the time constants of the ear because when we apply this sort of compression to a signal, whether we be instrument or voice, we are fooled into thinking it's louder than it really is. In practice, this works really well, and my own tests demonstrate, to me at least, that the number of signals individually compressed can be mixed without causing confusion. Of course, individual signal compression is almost always necessary for an artistic reason as well. It's needed to control the dynamic range of the loud parts and to make the quiet parts usable. That may sound obvious, but it's still essential for all but the most purist recordings. Joe Meek. When Joe Meek recorded lead vocals, his method was to drive the output of his microphone amplifier directly into a compressor, and from there into his mixer, and then onto tape. This worked well, and I've always done the same. In fact, that's the basis for the various voice channels that I have designed over the years. The P10, the mighty twin. To digress for a moment, the latest voice channel that's just finishing development will be a combination of mic amp compression with limiter function and with an equalizer. It will be a transformer-linked mic preamp followed by an asymmetric compressor that takes into account the way the human voice is very non-symmetrical, and then the EQ. An interesting feature is the variable phase facility. It is there to be able to tune the phase of the microphones that are close together, where there might be cancellation problems, particularly when recording drums. So the mic amp has a particularly huge overload margin so that high output mics close to the kit will be handled okay. Other signals. I have to suggest that it's generally not such a good idea to use compression on individual musical instruments, except possibly guitars in a pop music context. Some compression is often necessary, for dynamic reasons, when recording brass sections, but it's easy to get quite horrid results using compression on strings or most reed instruments. You can hear some early mistakes in this respect on records of the 1970s, where the producer tried to use the mellotron as an instrument. The results were uniformly horrible. And I think mainly because of the necessary heavy compression used to smooth out the dynamics of the instrument. Group compression. The most obvious and most effective use of compression is where you group together a number of sound sources into a subgroup and apply compression to the whole group at one go. The drum subgroup is the one that springs to mind straight away, and this is where creative musical compression comes into its own. It's always a good thing to have a drum kit sounding louder than it actually is. I'm tempted to say that it's difficult to overcompress most sorts of drums on pop records. I've seen them compressed to the most amazing extremes, and definitely the best sort of compressor for this is the slow photoelectric, like the Yuri LA2A or the old Joe Meek SC2, or its modern equivalent. A fairly slow attack time and a shortish release would sound too breathy on most things, but on drums it can give a depth and urgency and hold them stable so that they become the backbone of the mix. In my compressor designs, I always tailor the sidechain response so that the compression is less sensitive to low frequencies. What this means is that you can compress the whole kit with some extreme compression without worrying about the bass drum causing wallowing. In fact, you can even include the bass guitar within the same subgroup, making the bass and drums really tight. You could write in the same characteristics to a software compressor, but I can absolutely guarantee that it won't sound the same. Group compression is also very useful with vocal group recording. Here again, one can use some quite severe compression, but the release time is more critical because of how we hear the human voice. Any sort of flutter as the compression acts can sound very unnatural. The classics for a demonstration on the use of effect compression on voices are the Beach Boys and even more so, Queen. So there we have it, the first in this little series of lectures by Ted Fletcher, and I really do hope that you enjoyed that. For me personally, I really enjoy almost solidifying the foundation in what I'm doing. It might not consciously influence my studio decisions on a daily basis, but it's all there. You know, when you're adjusting the gain or, relative to this lecture, putting some EQ or compression on something, it's going to be there in your subconscious, all of this information. And for me, it's really important that I continually, A, remind myself of this so that it's still there, but B, get into the real nitty gritty of why those things are happening and why we make those decisions so that you can be informed musically. Using a studio is very similar to using a musical instrument. You're essentially applying parameters in a creative way, if you see what I mean. So different engineers obviously and different producers have their own sounds, and it's all to do with the addition of all these minuscule percentages that add up to create their sound. And it's really important to learn as much as you can, in my view, and to just continually gather information. So that's why one of the reasons I felt very strongly about putting this lecture series out. So yes, I really do hope you appreciated that, and I really do hope that you enjoyed listening to it. If you do have any questions at all, you can email me, joe@allyouneedisdrums. If I get enough questions, I will do a Q&A episode with Ted if he's willing to come and do one, which I'm sure he would be. So yeah, do get in touch. You can visit my website, allyouneedisdrums.com, where if you'd like to support the podcast, you can buy one of the beautiful enamel mugs that I have for sale there, as well as some of the music that I work on. You can also find all of the free drums that I give away and information on sessions and that kind of stuff. That just leaves me to say a huge thank you to you for listening. A thank you to Joe Kane for the intro and outro music, to Adam Mallet for the artwork he provides for this series, and to Rory Hancock for uploading the podcast and editing it and doing all of the legwork for us. I will be back next week with more from Ted Fletcher. Goodbye!